So I'm going to record a series of videos for our lecture on Chapter 10, Radical Reactions. This comes from David Klein's Organic Chemistry. Free radicals form when bonds break homolytically, and that's shown here in the figure. We've talked primarily about heterolytic cleavage. So hetero is a different cleavage, and that led to the formation of ions, a positively charged and a negatively charged species. In the case of homolytic cleavage, this is same cleavage, or the two pieces that leave have the same number. They each have one unshared, unpaired electron. And this is what gives rise to a radical. A couple of things here. We've used double-headed arrows to show the movement of electron pairs. And when we're showing the movement of single electrons, we use a arrow with one barb, or what we'll often refer to as fishhook arrows. And this shows the movement of a single electron. So in this schematic, a molecule is subjected to heat, and if the energy is of the appropriate quanta, the electrons will promote to an antibonding molecular orbital, and there'll be homolytic cleavage. And then just focusing on proper drawing of arrows, the arrow begins at the bond with the electron, and the fishhook arrow goes to the atom, showing that the atom receives one electron to form that radical species, and then similarly on the other side as well. Energy is required for homolytic cleavage, and that's always the case. So the bond dissociation energy will always be endothermic, a positive enthalpy, because it will always require the input of heat to cleave that bond. And we'll cover this again. Now, recall from Chapter 6, we discussed reactivity and the stability of carbocations. I just want to remind you, when we look at methane, we explain the symmetry and tetrahedral shape and equivalent energy of all four bonds by using orbital hybridization. So we have a sp3 hybrid orbitals. There are 4 of them, and they're formed from a s orbital and the 3 p orbitals. And the resulting hybrid is 25% s character and 75% p character. Now, looking at the carbocation, which is sp2 hybridized, we have 3 bonding pair of electrons. There are no other electrons, so the third p orbital is not hybridized, and it is empty. And the sp2 hybridized carbon is planar, trigonal planar. When we contrast that with the carbanion, we have a unshared pair of electrons that remain with the carbon in the carbanion, and it is sp3 hybridized. So there are it retains its trigonal pyramidal shape. This is a valence shell electron pair repulsion theory. Tells us that each electron domain will seek to have the greatest amount of space from the neighboring electron domains, and that's how we have the trigonal pyramidal structure. Now, looking at the radical species, just on the face of it, you might expect that it would behave intermediate between the trigonal planar sp2 hybridized carbocation and the tetrahedral sp3 hybridized trigonal pyramidal structure of the carbanion. And indeed, it does, either trigonal planar or a very shallow pyramidal structure that rapidly inverts. So this is planar and this is near planar. We can call this periplanar. Peri comes from the Greek word for near, so it means near planar or approximately planar. So I may refer to this as periplanar. Another thing I want to mention here is that the radical species is electrically neutral. While carbon does not have a complete octet, it does have its four electrons relative to its 4 protons, so it is electrically neutral. There are radical ions. They do exist, and when we talked about mass spectroscopy, we talked about the radical molecular ion, but it's most common for radicals to be uncharged. So, as I just mentioned, radicals are neutral, no formal charge, but still electron deficient. And as electron deficient species, they follow the same stability trend as carbocations. So we see that the methyl radical is the least stable. A primary radical is slightly more stable, but still relatively unstable. And moving to secondary and tertiary, the tertiary radical is the most stable. And this results from hyperconjugation with the neighboring carbon atoms. So when we think of bond dissociation energy trends, the bond strength is going to be inversely proportional to the carbon radical strength. The more stable the resulting radical, the weaker the bond, the easier it is to abstract that atom. So the bond dissociation energy for methyl is 435 kilojoules per mole, going down to 381 kilojoules per mole for the tertiary radical. And then further, like the carbocation, in addition to the similarity in geometry, the trend in stability extends to species that are stabilized by resonance delocalization. So the allylic and benzylic positions are able to allow resonance stabilization, and these will be even more stable than the tertiary radical. And this is an opportunity for some practice with the fishhook arrows. The radical electron moves to form a bonding pair with one of the electrons from the neighboring pi bond, which comes in, and this is a separate fish hook arrow to bond, and then the lone electron that's left moves to this carbon atom. So we have 2 resonance structures giving us additional stability. When we look at the benzyl radical, we have many more resonance structures, so this is further stabilized, and in the same way we can draw the resonance structure showing the radical electron occupying a different location around the ring, giving us these 5 resonance structures. And remember, the curved arrow originates from the radical electron or from the pi electrons. And then reiterating, this additional resonance stabilization results in a lower bond association for the allylic and even lower for the benzylic radical. The vinylic radicals are going to be less stable than primary radicals and significantly less stable than the allylic radical. Similarly, the aryl radical will be among the least stable free radical. So these trends are essentially the same as what we observe for carbocations. Compared to carbocations, we saw a similarity in geometry. We saw a similarity in their relative stability. The reactions are going to be different, but I guess the one thing that's similar is that the reactions of radicals follow distinctive patterns. And we're going to go over 6 key arrow pushing patterns, and David Klein has done a nice job of organizing this so that really we're looking at 3 reversible, 3 forward and 3 reverse versions of this to get our 6 arrow pushing patterns. The first of these is homolytic cleavage, and this is initiated by heat or light. This is common for oxygen bonded to oxygen or dihalogen species, also for azo species, which so an azo compound is going to have the general structure. Oops. And these are the subject of homolytic cleavage. The second arrow pushing pattern will be the addition of a radical species to a pi bond. The third is hydrogen abstraction. Now, remember, this is not the same as a proton transfer. There's also halogen abstraction. These two are quite similar. The elimination reaction, which is the reverse of the addition reaction. The radical on the alpha carbon is pushed towards the beta carbon to eliminate a radical atom or radical group. And then coupling reaction, and this is the reverse of the homolytic cleavage. And in the beginning, I mentioned that homolytic cleavage is always endothermic, and this coupling reaction with the 2 radicals coming together to form a bond, it will always be exothermic. So what we want to remember is that the homolytic cleavage and the coupling reaction can be thought of as opposites of each other. So that is one of our arrow pushing patterns. The addition to a pi bond and the elimination to form a pi bond are also can be thought of as 2 sides of the same coin. So that's the second pattern for us to remember. And then the hydrogen abstraction and the hydrogen abstraction and the halogen abstraction can be thought of as 2 sides of the same coin. So these are the 3 arrow push. There we go. Clean that up a little bit. So the reverse is the halogen abstraction. So now let's look at these patterns in a little more detail. Let's start with our radical initiation step. So an initiation step is any step where there's a net increase in the number of free radicals. So generally this comes from some application of high energy, either from heat or light. Usually light in the UV range is in the right level of energy. And we're going from a net of 0 radicals to 2 radicals in this step. So this is an initiation. We have propagation, and a propagation step, there's no net loss or gain in the number of free radicals. The identity of the radicals is going to change, but the number on the product side and the reactant side is the same. So there's no net change in the number of radicals. So when we have addition to a pi bond, we still have the radical species. When we have abstraction, we have a radical species. When we have a halogen abstraction, we still have a radical species. And in the elimination reaction, we form a pi bond, but we still have a radical species. So there's no net gain or loss in the number of radical species. And then in a termination step, there is a net decrease. So it's the opposite of the initiation. We go from two radical species forming to form a non-radical species. Remember the change in the number of radicals as part of defining what a initiation, propagation, and termination step will be, and we'll discuss that coming up in a few more slides.